Hi, everybody. I'm Glenn Johnson with NASA Hunch Design and Prototype, and we are talking with Luke Sammons today. Luke, could you tell us a little bit about yourself?
Of course. I actually started off in design and prototype. I think it was my sophomore year of high school. From there, I then ended up going on to flight configuration, which, funny enough, is actually the current group I'm working for inside of Hunch. Graduated from high school, interned with Hunch all throughout college, graduated with my bachelor's in mechanical engineering. I work for NASA Hunch, and in particular, I am a flight configuration engineer. So more or less, it's just the next step after design and prototype is what flight configuration does.
Okay,
So think
so
about
what kind of things do you work on for Flight Config right now?
so predominantly what I tend to work a lot on is think about drawings and other things like that. We just went through and finished up a table and everything else. It's called the HUD or Hunch Utility Desk, and it's meant to be more or less used for writing or just general utilities by the crew of the ISS.
Now, you've worked on a lot of projects with us. Some of them have flown and some of them have not. So, for example, like the ball clamp monopod, you did a lot of work on that as well, right?
Yes, sir, that's correct.
What did you do on that? What was your specific tasks?
So a lot of it was already done by the time I kind of came on board. More or less, what I did is a lot of finishing up and doing final drawings and other things like that. Because what typically happens, and at least on our side of like configuration, is we take the initial prototype and everything else, start working on making a fabrication model, fabrication level drawing. Then we actually go through and our manufacturing group at Hunch will go through with our students, machine out all the flight hardware, and then do the finalized flight drawings. So by the time that I kind of came on with Hunch, I ended up going through and I did a lot of the final drawings and everything else for the monopod ball clamp.
And this is before you graduated from college. So you worked as an intern with us, but you had your name on drawings that are now used at NASA every day, right?
You're spot on. So for the monopod ball clamp, that was actually my freshman year of college whenever I went through and I worked on that drawing and I had my name on that. And the neat thing is, it's not even just, say, for example, me who did that. I know that some of the other students that we've had that have gone through Hunch, one that comes to mind in particular is Wilbur Garcia. His name is on the official drawings for something else we have called the Hunch Utility Bracket, or HUB.
Yeah. That's terrific. Now you're working on some new stuff. What kind of new things are you developing now?
So originally, whenever I came on, we were underneath ISS, which is International Space Station. Now that since we're on Moon to Mars, I'm currently working on some different things for Starlab in particular. I'm working on as well as some other different things for Gateway. To give you an idea, we have for Gateway, we are actually going through in the process of designing a new payload enclosure, as well as going through and for Starlab, actually currently in the process, and I got done with it earlier today, doing some of the different models for manufacturing the mock-ups for the Starlab actual racks that all these payloads are going to be going into.
So this is a trainer rack that you're designing right now, but later on they'll probably make some changes to it, and that'll be what flies to the moon in the Gateway space station, right?
You're spot on with that. So the current rack that I was working on, more or less, I took the previous models and other stuff like that from somebody else.
Just because I can see behind you a little bit, can
Mm-hmm.
you just point out for our students what kind of equipment you've got right behind you there?
Gladly. So I can point out that as well as some of the hardware too here in a minute. So right here we have a 3D printer for going through and doing some basic prototype. Bamboo Labs. I'm sure a lot of different students are familiar with that. Wonderful printer. Our Mark Forge 3D printer right here. That's great for doing carbon fiber, as well as some other different things. It's kind of hard to see, but that blue thing over there that is a laser cutter that we have where we can go through and engrave aluminum, all kinds of other fancier things. And you can see part of my three monitor setups, but in particular, this rather large box right here is a very, very fun printer. It's our Stratus 450. And the neat thing about the 450 is it allows us to go through and print some very, very unique plastics for flight, such as Ultim, which is one of the really big ones. So it's just a little bit weaker than, say, aluminum. And it's a plastic.
Wow. So why do we want to use Ultem rather than aluminum then? What's the value of that?
So part of the reason why we would want to go through and use Ultim instead of aluminum is, first of all, we can go through and 3D printing Ultim, even though it's more expensive than a lot of your other materials. it is way cheaper than going through and 3D printing aluminum right off the bat.
Yeah.
So more or less just for manufacturability, as well as the fact that it's cheaper. Because if we want to go through and let's say that we have a bracket or something else like that, I don't know if I have any lying around, but I can show this. So this little guy right here it was a prototype of a camera shoe.
Yeah.
So exactly. Has these little slots, and this other little thing right here has this backwards geometry. Although it's a relatively small part, this right here would take significantly longer to go through a machine on a mill than what it would to 3D print this. So to give you an idea, this might at most be like a 2-hour print if I had to guess on the Stratus 450, probably underneath that. For a machinist to go through and set up for that as well as mill it out, it's going to end up taking him a lot longer than 2 hours. So essentially, it's about having faster turnaround times.
Yeah, and on the order of days potentially, right? Or at least
exactly.
a day. Okay, and that particular part was actually designed by one of our students up in Conroe High School. So that's actually a really cool part to show as well. Okay. All right. So today I asked you to come on and talk with me about the jumping robot. And what's special about the jumping robot and you is when I was developing this, I was talking the whole time about, hey, what do you think about this? And so I thought it'd be great to be able to have you and me talk about this, and you could give some of your pointers to what you think might be helpful for our students. Is that all right?
Sounds wonderful to me.
Okay. All right. So we're looking at the first page here, and it's just kind of the introduction. Now, have you been watching the performance of this helicopter that JPL had sent to Mars?
I'm afraid I haven't been, to be honest with you.
Right.
I've been pretty much. Well, the thing is, I've been pretty much living underneath the rock for the past several months, if I'm being honest. So I'm afraid I missed it. I've heard about it. I know that it's something that was occurring, but aside from that, I honestly have not.
And that's okay. I mean, the point of it was just, they turn on this helicopter. It flies above them. It helps them look at the surrounding rock strata and whatever, and then be able to drive the rover over there to be able to look at whatever it is that they thought might be interesting. But the difficulty here is on the moon, there's no such thing as air. So helicopter will not work, but this jumping robot might. Now, the original idea from of this, he's a professor at UC Santa Barbara. The question is, could we adapt this idea, because this was mostly his idea, to be able to turn it into something for the moon and have our students work it? And you've seen some of these ideas. Now, the problem is, whenever I work on these things, I know that I can't build it. Because if I do, it will taint what I look at for the students. Because I want everybody to do my idea. Now, you have completely different ideas than I do on some of this. Did you have any thoughts when we started talking about this, about what you thought would be a good idea?
I did. So what I lean kind of more heavily on and other stuff, and that's I keep on leaning back on this idea of is using springs of some sort. But my only concern with doing that is think about how much it is that on the lunar surface temperature changes, right?
That's right.
I think is it 200 degrees plus and then 200 degrees minus. I forget what the temperature swing is, but
and it's I rounded off to 250 plus and negative 250 minus, but that's not accurate. If you look it up, you'll find that it's a little bit different. But that's a huge temperature swing, and you can imagine that for something like a rubber band or something like that, there's no way it would work on the moon.
Exactly.
Now, what about a spring? It's still difficult, that's for sure. But is it more likely to find a spring material that'll work for those kind of temperature changes? Probably. More likely. So what are you thinking about?
So that was pretty much what I was thinking about going through, is using some sort of spring mechanism, and more or less I forget what it was. It's a particular type of bug. Let me see if I can figure.
Yeah. What kind of bug are you thinking?
So that's part of the promise. I can't remember the name of it, but essentially it uses a kind of spring mechanism like that to launch itself into the air. And the easiest way to explain it is think about if you had, say, I'm just going to pick up random things I have lying around here.
Yeah.
So let's say, for example, that you have a stick right like this, another stick right like this with a hinge joint
Yeah.
right here in this end. So the way that they kind of use it to fling themselves is they have a spring right here that they go through and they load up, and then they have these kind of hairs that kind of hook together, and then think about it almost like Velcro, sort of. And what happens is they go through and they load it up and they load it up and they load it up more and more with their muscles till all of a sudden, right here, these hairs give, and the Velcro essentially comes undone, and it causes it to also just spring away.
Wow. That's really cool. Okay. So is it like a grasshopper of some kind, or what are you thinking?
It's called a frog hopper. So it's this little bitty insect. It's about that big. They're roughly about a quarter of an inch, and they're not anything that's super large. And on top of that, they're super common. But even though
Okay.
it's only about that big and a quarter of an inch long, they can jump about 28 inches straight up in the air.
Holy smokes. Okay.
Mm-hmm.
Now I
They're
found a
called a
picture.
frog hopper. And
Yeah.
if you take a look, look up their leg mechanism in particular. That's a really, really interesting one, and that's kind of how they get their name is because of how their legs look. And much like a frog, they kind of have, if you're, say, for example, you're just looking at one leg, it comes off the body, goes forward, and then goes backwards. And it's right up here where it has that little bit of Velcro that I was talking about that connects to the body. So what happens is back here on this end, it loads it up and loads it up and loads it up till eventually this Velcro gives away and it breaks here, and then it launches.
Okay.
They're a very, very interesting little insect. So one of the other things that you can also see with them is because you can imagine with how fast those legs are going to be shooting down because they jump per their body length, one of the highest, if not the highest jumping insects.
Wow. Okay. No, that's
Because they're
terrific
jumping clear
advice.
over 100 times their body length. The crazy part about this is they actually end up accelerating with about 500 G's of force. So you can imagine those legs shooting out that fast they kind of have to be timed just right. So one of the
Yeah.
really neat and interesting things you'll see about them is where it attaches to the body. These two legs, they're actually geared. It's the
Okay.
only known gear that is found naturally within nature, and it's a true gear joint in between these two legs to make sure that they go at the right timing.
That's incredible. So one of the things that we've got to worry about though is not just a jump, but it's going to fall, right? How do you
Exactly.
survive a jump over and over with landing on the moon? It's not like we get to land in grass or on a carpet or anything. So, this makes it difficult, right? Now, yes, it's 1/6 gravity. I'm asking students don't go over 10 feet on Earth because I don't want to get people hurt. But
Exactly.
falling something like 10 feet, that's survivable. Did you have any ideas of how you would make it so that it would survive over and over?
So since you have low gravity, I think one of the things that you can get away with is I don't know how to explain it other than not a ton of them, but think about whatever the almost exterior shape of your robot is, since you don't have to worry about drag at all. What if you had a bunch of really long, stiff bristles? So, say, for example, like 2, 3 inches long or something like that, and they stuck out all over the sides and everything else. Let's say, for example, you just had about 30 coating the entire thing. So that way, whenever it comes down, these bristles, they bend and they themselves will kind of act like a spring and will kind of hit and absorb it and then cause it to kind of move some.
You
Since you
remember
don't have to
those?
worry about all the air friction.
Do you remember those cush balls? It has a whole bunch
Yes,
of. That's kind of your idea, right? That's
exactly.
actually really smart. That's a good thinking. Um, Now, another option though, or the other problem is it has to right itself and then be able to jump again. And so, can we do that by weight so that it's kind of bottom heavy? Or, you know, the shape of your little spine things, could that also help with getting it righting itself for the next jump? So I don't know. That's a really nifty idea, though. I like that. Um,
With the bristles, I don't necessarily know that I'd get it all the way, but I do think that you could probably get it a lot of the way back. at least to the 50% point of it being back and everything else, just automatically from those from that same mechanism that's using it to kind of slow itself down. Because my
Yeah.
thing is, your legs on the bottom, if those hit the ground, for example, they can bend and they can buckle, and that'll help take a lot of your load. Having those other kind of spiky bristles all over it, that causes it. So, say for example, you have a bunch that are really, really long on top, and some that are shorter, like kind of towards the side where the bottom legs are. All of a sudden, it'll kind of hit on these and force it to kind of go cattywampus towards the bottom. Would kind of be the goal.
Yeah. No, that's good thinking. I like that. Here,
Sounds good.
I'm just talking about some of the difficulties of taking off and landing on the moon. From on orbit, it looks relatively smooth. But of course, you get down to the ground there and we start talking about rocks. We start talking about whether they're baseball size or they're, like armchair sized, those are some pretty significant rocks. But that's also why if you have a rover that's driving around and then shooting a camera up, you can't get everywhere with a driving rover because these rocks are going to be in the way. And that's part of the value of having a robot where its sole job is to jump because you can jump over a lot of big rocks. How do you make it so that when it jumps, it's going in a specific direction as opposed to a random direction? So that's a difficulty with a jumping robot. Now, just to be clear here, students I did not give that as part of the project because I think that that's actually difficult. But if they have the answer for that, they can do it.
Yeah, I don't know. That'd be kind of part of my big concerns. I don't know the way to do it well within the weight requirements.
That's right. And that's also part of why I wanted it to stay. I want them to keep their robot lightweight so that they can get the jump out of it that they're looking for. All right. So now we're on slide 3, and I had put together kind of a collection of how students could arrange different teams if they needed to. I mean, I'm hoping that everybody wants to make a full robot, but I was trying to suggest, hey, these are ways that you might divide up your people so that you all have jobs. I don't know. Any comments to any of those things?
So I would definitely say go ahead and take the approach of divide and conquer by all means. I agree with you completely on that because otherwise it's definitely a lot to go through and do.
And I've got a couple of pictures there on the side. Did you have any thoughts about those? That top one kind of reminds me of what you're talking about a little bit.
They're definitely a little bit different of a mechanism and how they work, but that was just a potential idea that I remember, well, more or less thinking about jumping robot. I was like, well, I remember there happens to be an insect that had some crazy jumping mechanism, and that's what it was. It happens to be those, and get something to move 100 times its body length in pretty much no time flat. That's
Yeah.
going to be a very, very effective jumping mechanism that's going to require very little mass and end up yielding a ridiculous amount of force.
Now, when you were working on your bachelor's degree for mechanical engineering, right?
Yes, sir.
Did you have to do any kind of controls? Did you guys use some small computer systems or anything like that to be able to make stuff for your projects in class?
We did use some of that, but at least for me in particular, what I was more or less geared towards was, say, a fluid dynamics, heat transfer, and then stress analysis. In particular,
Oh,
on
okay.
my end, the stress analysis side, because that's
Well,
just what I have more of an interest in.
sure. And that actually fits along with, some of these other projects like the energy storage, but also the body as
Mm-hmm.
well, right? I don't know if you had any ideas about the body, just because the falling thing, I really like your idea of the finger, the little spiny things. I think that's a great idea. Any way you can spread out that force, I think is a terrific thought.
So once again, kind of sticking with this entire theme of insects, another one that might be good for students to go through and take a look at is kind of like how the shell of an ironclad beetle works. So it's a little beetle about this big, but you can drive over it with a car and it won't crush it. It can get up and
Wow.
just walk away perfectly fine. And it's due to how the different layers of its shell interlock like a puzzle piece.
Really?
So
Say that
maybe
name
that's something
again.
that could ironclad beetle. In
All right.
particular, see if you can find one that's kind of well, I just looked it up. It's specifically the diabolical ironclad beetle. You can
Gotcha.
find images of how their shell kind of interlocks and interweaves, and it looks like a puzzle piece almost.
Okay.
And my thing is, I mean, a super, super tiny insect, yet they can hold just incredible amounts of weight. You pretty much
Wow.
can't crush them.
So then on slide 4, we're looking at, you know, the maximum that we want them to jump is 10 feet.
Mm-hmm.
Um, now, and I would be very happy if we had students that were able to get up to 6 feet, because when you get to the moon, that's, at around 36 feet. That would still do a pretty good job. Um,
Absolutely.
Now we have a couple of different ideas here, though. Um, I mean, different flexible materials, using springs. You know, it's funny. The one at the top, it looks like it has springs at the elbows or kind of the knees or whatever there. Does that make sense?
That's what it
Um,
looks like. Yeah.
and so they've got two springs as opposed to like the other one that we saw on the first page. It had a big long spring in the middle. And so just different ways to come up with how to use that force.
So I would personally kind of lean towards maybe not either one of the way that those particular two operate, but if at all possible, if there's a way to get away with, say, one spring that's stiffer or something like that, so that way it's simply just less weight. But that would largely depend on how your mechanism works and a bunch of other different things like that. And truth be told, it may not even be possible with some different designs.
You're right. The spring is going to be made out of steel most likely, and that's
Mm-hmm.
probably going to be one of your densest materials. So trying to get small ones or just one is probably a smart idea. That's a great suggestion.
Exactly.
Okay.
That would kind of be my thing is go with a spring or whatever in the world that's just super, super stiff versus two springs, if possible. Like I said, it'll kind of depend on the design a lot.
Here, I was just trying to react to some of the questions that I've gotten from students. Um, if your robot can jump 10 feet, translate across the moon's surface. Yeah, translating across the moon's surface, I didn't want to make that a requirement, but if students are going to come up with ideas, I'm open to it. I mean, part of the difficulty is that we're looking at a surface that is going to be very random. So if you have
Yeah.
legs on it, one leg can be on a rocket and it'll send you this way. Another time it's going to land and the rock is on a different side and it sends you opposite direction. So, I mean, I don't know. It seems pretty difficult. Have you had any thoughts about that?
Is I'm sure you've seen those what are they called? Like those little cubes that you'll see people build, like college students, that flywheels on the inside that'll allow them to go through and let's say, they'll start out flat like this, then they'll stand
Uh-huh.
up on this edge and they'll stand up on a corner. Something like that. But my issue is I don't know of a way where you can do that lightweight.
Yeah, because you're talking about little flywheels inside, and those could be kind of heavy.
Exactly.
Yeah, that's interesting. Yeah, good thinking.
So there has to be a different way, or maybe there's potentially some way. Because I mean, if you have gravity, you're always going to end up knowing where down is if you have just like a little bit of liquid on the inside. But I don't know of a good way to kind of consistently do that because then part of my concerns ends up being, let's say there's a rock here or something like that, and it kind of lands up against the rock and it can't fully right itself how it needs to.
Yeah.
It can't go all the way back. It just kind of stops. So
Now,
that's a very, very difficult one, I will say.
sure. Now, one of the other difficulties they have is at least some of these, they put their camera up top. But if you've got your camera up top, it means that you're taking that the body of your robot is going to block your camera view. And so,
Yeah.
you know, there's nothing that says it has to be up top. It's very possible for it to be down low and still be able to get a good picture. And you got a cable on that thing. So you might stretch that cable as far as you can to get as much good picture as you can. How the robot will be used, I tried to make it as simple as possible. I mean, um, I want the astronaut to be able to pick up this robot, walk outside with it, drop it in a location, get away from it before it jumps, and then let it operate on its own and then go pick it up later. you know. Um, and then being able to have the picture sent to a phone or something like that, just trying to keep it as simple as possible. Um, I don't know. Does this fit the way you think we would operate this?
I would definitely have to agree with you on that because, I mean, take a look at, say, spacewalks, for example. The primary goal of spacewalks is to mitigate the amount of, well, aside from, whatever in the world is they're actually doing on the spacewalk, you're trying to go through and mitigate the amount of time necessary for every single action. So if you can just set it up and then functionally how to put, not really forget about it, but you set it up, leave it be, go do whatever in the world it is that you need to do since you're already going to be out there and you're going to have a list of tasks to go through and complete some of those or complete all of those. It'll go through, send all of its stuff. For now, to the phone works great. I'm sure that you more or less did it with the intention of at a later date, it would be, say, a server or something else inside of
That's right.
the moon base. And then from there, after completing the task, all they have to do is just go grab it, and then that's it.
Yeah.
Hoping to minimize crew time. I definitely think that would be the best way to go through and do it.
Now, one of the difficulties we're going to have is if we set it up and let it go, we're going to have to find it somehow. So I'm not sure what that's going to look like yet, but if students have an idea of how we're going to find that robot after a while, that could be helpful too.
I definitely think that would be helpful. And part of my thing is if it's already linking back to some sort or form of server, then I don't see why in the world it wouldn't, but I don't see that it'd be very difficult to have some way to kind of just determine its approximate location. Because,
Yeah,
I mean, if you're within, say, 10 feet of it, you're probably going to be able to find it pretty darn quickly.
I bet triangulation just from the signals will probably give us a pretty decent idea. So I also did not make that a requirement. So safety. This was one on my mind here. I don't know if you've ever been smacked by. Oh, look at that! I got one. So I got a rat trap right here, and I'm very careful to not let myself get smacked by it. Mouse traps hurt enough, but that had hurt a lot. So, anyways, that was part of the reason for the 10 feet requirement. And in some cases that might actually still be a little bit high. But anyways, I don't know if you've been smacked by a mouse trap, but I've had my share.
So, and for the sake of all honesty and transparency, I have been smacked by one of the little ones, but that's because, I mean, I think at a certain point in their life, everybody does something really, really stupid or knowingly does things like that. And I got curious once and it didn't feel the best.
When I was a high school teacher, we were doing mousetrap cars, and somebody set up one of the mousetraps on my desk and didn't tell me. Found it. It's funny. The student came up afterwards and said, "I'm really sorry, Mr. Johnson." And I said, "Yeah, it's okay." He really didn't mean it. And one of the difficulties here is lightweight. To be able to get this thing to jump very high, we're going to have super lightweight little robots. And so I was just talking to one team and they were talking about it being 1 kilogram. And I thought, wow, that's a lot of weight. I'm hoping that they'll be able to cut it down a little bit. Any
Yeah,
thoughts
I think
on
1 kilogram's a lot. Well, I mean, you have to think about it like this. 1 kilogram coming down from about 10 feet up in the air, that darn thing's going to be heavy.
Sure. That'll hurt.
You've got to be really, really careful where that comes down. So, and my other thing too is on the weight, trying to keep it down as much as possible because the less weight you have, then the less force you really need to launch it up in the air. So, in terms of materials, I would definitely say try to stick towards really, really thin stuff. So, I see like one of the things that you have on there is soda cans. To me, that's a pretty good idea for going through and mocking it up because if you need a very flat part, but yet you still want it to be stiff like in metal, well, you can go through and do exactly what you have on there. You take a soda can, you cut it open, now you have a very, very flat, thin piece of sheet metal.
Yeah. And bottles as well. I mean, they're pretty darn lightweight as well. So yeah, I'm looking forward to seeing as much lightweight stuff as we can.
By all means, for your prototypes, if you want to say in your final design that you want it to be Ultim, that's great. Print it out of something that's cheaper, print it out of something that's lighter. If you can get the idea across with a piece of cardboard, use a piece of cardboard.
So when you start up a new idea, what web page do you go to for your beginning ideas?
No matter what you do not go to the computer first and start doing CAD. Take a
Okay.
whiteboard and a darn expo marker, mark the entire thing up, come up with ideas on there, take a pencil to paper, all kinds of other things like that, because the result has been, I mean, there's been countless times you and I have gotten together in the span of 20 minutes. We'll sit there and we'll come up with, 15, 30 different ideas. I've been doing CAD in an Inventor for, shoot, I'm going on year 9 now of doing this since I started as a freshman in high school. I've been using the same program this entire time. I've learned a couple others, but for the most part, it's been Autodesk Inventor, and I can't even do it that quick. So by all means, I heavily, heavily encourage, and I would definitely push for your initial ideas. Take a expo marker to a whiteboard and just start drawing stuff out.
Yeah.
Do that, and if you want to, I would encourage. You might forget about some different things, so maybe take a photo of it, so that way, if the next class comes through the classroom, they're going to end up erasing it. But now you have a photo, you can go through and look back on it.
Yeah, that's good. Well, and I was thinking about McMaster Car. I mean, I really like going to McMaster Car just because it has so many examples of things that already exist. Start with something that's kind of what you're looking for, and then see if we can build on it and make it better for our application. But yeah,
I agree with you completely.
Sketching first.
Don't get me wrong. I love CAD. I use it nonstop, literally daily, both for work and for personal stuff. But at the end of the day, sketch it first. But in terms of websites, by all means, McMaster Car. So
yeah. I don't know what it is about hinges, but I've seen a lot of people design their own hinges. I'm not sure why. There's a lot of hinges out there. But the point is, this one's going to be a lot stronger than one that you would 3D print as well.
Exactly.
And I can still modify that hinge if I want. Okay,
Oh,
on
definitely.
the last page here, we're looking at, I gave some requirements to make it a little bit easier for how we're going to test it. This moving blanket for $5, and I don't care what kind of moving blanket they use. If they've already got a moving blanket, that works. But that gives kind of a dimension of how, the robot does a jump, it falls down within that area, and then they do a second jump. Now, if it goes off of there, I'm okay with that, but just realize it may break. And it's not that this pad is so terrifically thick or anything like that. I just wanted something that was easy that teachers would be able to find. How would you test your robot, do you think?
So I do really like the idea of having a pad. One of the other things that I was thinking about is, the Lunar surface for the most part is very, very similar to sand or something else like that. And part of my concern with it would end up being is, say, for example, if you have a robot that has a very, very small kind of footprint, if you have your sand and it goes to go ahead and push down into your sand, your foot might just straight up go through the sand. If it has a larger surface area, it should not go through the sand and it should actually be able to push off of it more. Yeah. So in addition to going through and of course testing like this, and by all means, I do encourage the students to hopefully end up breaking some of the different designs in this testing. Testing till failure is a wonderful thing, even if you do it unintentionally, which I do all the time. Exactly. You learn more from failure than what you do success. So by all means, failing is a very, very wonderful thing in a lot of different ways. I encourage it whenever it's on designs and other things like that.
Yeah. No,
but I would definitely also say for them to go through and take some sand and put it inside of something else, not necessarily to test jump height, but to make sure that their foot or whatever their surface area that's pushing down on their sand or whatever the flooring is, it does not more or less just stick itself into the sand.
Yeah. That's a great comment. And, so last year, we ended up carting around a lot of sand, and it was a lot of trouble. And that's kind of why I went with the pad. It's a little bit easier to move it around. And I ended up with a lot of sand in my yard this past year.
I hear you. And like I said, for actual testing on height, I definitely think sticking with the pad. But I just think that it's another idea worth considering for the students to think about kind of on their end. If we go through and we have this mechanism that's going to spring itself up, is it going to only spring itself up a little bit and bury itself in the sand at the same time?
Yeah. Okay.
So just more or less something that they can do on their end to test it and consider it. But for the actual testing, no, by all means, I think use a moving blanket like this for at least height testing. because it'll have a little bit of give. The sand itself will have a little bit of give. It's close enough for that. And then essentially, hopefully, it'll help mitigate sand going everywhere else, because I know that last year we got a decent bit of that inside of, why am I blanking? Rocket Park, and you ended up with a bunch of excess in your yard and all in your vehicle.
I was vacuuming my van for a very long time, so.
Oh, I bet so.
All right. Well, thank you so much for spending some time with me on this. I think this is really going to help out some of our students. And I may be asking you for more help as we go through this, because I think you're going to be coming around and helping us out with some of our design reviews. So I look forward to the students being able to meet you too.
Sounds great to me.
All right. Thanks a lot, Luke. I'll talk to you soon.